The last two questions in this chapter, we'll do some capacitor questions. The first one without and the second one with a dielectric in. So we've got two electrodes that are square. They're 2 centimeters by 2 centimeters in size. Okay, so we've got 2 centimeters on each side. And the distance between them is 0.50 millimeters. And they're connected to a 100-volt battery. We want to know what's the capacitance, how much charge is stored, and how much energy is stored. All right, so capacitance, the equation is C is equal to epsilon naught A over D. Epsilon 0 is 8.85 times 10 to the minus 12. It's just a constant. A is the area of the plate. So the area of the plate is going to be length times width since it's square. And remember, we've got to put it into meters. So 2 centimeters is 0.02 meters. So length and width are the same as each other. So I get 4 times 10 to the minus 4 units or meters squared. The distance between the plates is 0.50 millimeters. So that is 5.0 times 10 to the minus 4 meters. Because remember, there's 1,000 millimeters in a meter. Okay, so now all I have to do for A is just plug and chug those numbers. So C is epsilon naught 8.85 times 10 to the minus 12 times A, 4 times 10 to the minus 4, divided by D, 5 times 10 to the minus 4, and I get 7.08 times 10 to the minus 12 farads, which I should round to 7.1 times 10 to the minus 12 farads because I've got two significant figures in all my numbers. And so I could also say that that's 7.1, and the SI unit for 10 to the minus 12 is pico, so I can write that as picofarads. Remember, 1 farad is a very huge capacitance. Usually you'll see micro, 10 to the minus 6, nano, 10 to the minus 9, or pico, 10 to the minus 12 in a real circuit. All right, so for part B, we want to know how much charge is stored on the capacitor. So we have the equation Q is equal to C times V. So Q is what we want. We just found C, and we know V. So again, all we have to do is plug and chug. These capacitor problems are pretty much just straightforward like this. So C, let's put in our 7.1 times 10 to the minus 12 farads times our V, which we're told in the problem is 100. And we get 7.1 times 10 to the minus 10 coulombs is the amount of charge on the capacitor. All right, so finally, how much energy is stored on the capacitor? Well, remember we had these three equivalent equations. U is equal to 1/2 CV squared, or U is equal to 1/2 Q squared over C, or U is equal to 1/2 QV. And again, you choose based on what you're given in the problem and what you have. We could actually use any of these now because we know Q and we know C and we know V. Let me use just the first part, okay? So I'm going to use U is equal to 1/2 times the capacitance, 7.1 times 10 to the minus 12, times the voltage, which is 100. If I do that, I get 3.55 times 10 to the minus 8. We take that to 2 sig figs, 3.6 times 10 to the minus 8. And it's energy, so the units are joules. Okay, so again, pretty much straightforward. All right, let's do one now where we put a dielectric in. All right, so now I've got circular electrodes that are 2 centimeters in diameter. Get my numbers. Okay, so they're 2 centimeters in diameter. All right, so I know it's 2 centimeters all the way across. And remember, I'm going to have to find the area. Area for a circle is pi r squared. And in this case, r is equal to half the diameter, so 1 centimeter or 0.01 meters. So it's pi times 0.01 squared, which is 3.14 times 10 to the minus 4 meters squared. Okay, so that's the area. What's the plate separation? We're told that they have a 0.1 millimeter thick sheet of Teflon in between them. So the D is just going to be equal to the thickness of the Teflon, 0.1 millimeter, or 1.0 times 10 to the minus 4 meters. Okay, so I've got area. Now remember C, if I've got a dielectric in there, is equal to kappa times epsilon naught A over D. And we're told that we have Teflon has a dielectric constant of 2.0. So kappa is equal to 2. And what else are we told in the problem? Blah, 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 blah. Connected to a 9-volt battery. So V is equal to 9.0 volts. All right, so I want to know what is the charge, the potential difference, and the electric field in the capacitor before and after the Teflon is removed. Okay, so initially we've got the Teflon in there. So we're going to use this equation. So I want to know charge, potential difference, and electric field. So Q is equal to CV, which is equal to kappa epsilon 0 A over D times my voltage. So I've got 2 times 8.85 times 10 to the minus 12. That's the constant for epsilon 0. My area is 3.14 times 10 to the minus 4 meters squared. And the distance between the plates, 1 times 10 to the minus 4 meters. And the voltage, we're told it's a 9-volt battery. So I get a charge of 5.0 times 10 to the minus 10 coulombs. Okay, so what else do we need to find? Charge, potential difference, and electric field. Well, the voltage, of course, is 9 volts because it's hooked up to the battery. And the electric field is V over D. So that's 9 volts over 1 times 10 to the minus 4 meters. So I get 9 times 10 to the 4 volts per meter. Okay, so that's with the Teflon. And what happens when I take the Teflon out? Well, what's going to happen is that instead of having my equation with the K in front, now if I take out the Teflon, so with the Teflon, K equals 2. If I take it out, then I just get back to air, which has a K is equal to 1. All right, so without the Teflon, Q is equal to my new value for C, just epsilon naught A over D times V. So 8.85 times 10 to the minus 12 times area, which is the same. The plate separation is the same. All we did was take out the Teflon. We didn't move the plates further apart, times 9 volts. So I get 2.5 times 10 to the minus 10 is my charge. Voltage is still hooked up to the battery, so it's still 9 volts. What's my electric field? V over D, so 9 over 1 times 10 to the minus 4. So it's 9 times 10 to the 4 volts per meter. So what actually changed? Well, because I left the battery connected, the electric field is the same, the voltage is the same, but the capacitance decreased by a factor of 2 when I took out the Teflon. So since the capacitance decreased, the charge also decreased by a factor of 2 when I took the Teflon out.